We're relatively new to fuzzing, and I'll talk a little bit towards the end of the presentation how we got into it in a particular issue that we were trying to address. So just a quick overview on why we do what we do. And a picture's worth 1,000 words. And so our surgical robotic system is geared towards benefiting the patient in a way where we provide less trauma during a procedure and give them kind of the best experience they possibly can, even though having surgery is not something that's typically pleasant. But as you can see on the left-hand side, the traditional way of doing heart surgery is to a large incision down the chest. That resulted in large amount of time for recovery, and there was a lot of patient trauma and pain. On the right-hand side is what our device helps to enable, and it leverages minimally invasive type techniques, which have been around for a while, but ours then provides the ability for dexterous manipulation inside the body, three-dimensional view of the operative site, and I'll go through a little bit of the system and the different components. As we walk through and address different areas of medicine, one that's recently come up is TORS, transoral. It's a process where they use natural orifices of the body for an entry point, which is really the most minimally invasive you can possibly get, because you don't even have single scars on your umbilicus or other ports within the body for instruments. And so we've been able to take the small miniaturization of the instruments and be able to use those in a variety of procedures. So just a quick overview of the system. We've got a surgeon console, which I show two there. Our most current model has the ability to do some mentoring. That'll lead into some of the applications for remote types of features that we'll talk about in a moment. We've got the patient side cart, that's where the business end is. That rolls up to the OR table, and that's what holds the robotic instruments. And then we've got the vision cart, and that's where all the vision processing occurs. It's also where all of our network equipment and capabilities are. I'll walk through some of the applications that we have, but all of the hardware and processing that enables that is housed in that subsystem. So what wasn't shown in that last picture is really the where surgery happens and the devices that enable it. So you can see on the left-hand side, those are the robotic instruments. And what I mean by a robotic instrument is, unlike handheld laparoscopic technique, which some of you might be familiar of, they use what we call chopsticks, where you insert the instruments and the only thing you have is grasping. So if you want to reach around some anatomy, you're having to move your arms and try to reach the surgical site. With the robotic system, we have full articulation of the instruments, and so it allows you to reach around anatomy and get to where you need to go. And then the upper right-hand corner is the 3D view, where we have a dual optical channel, which provides a surgeon with a three-dimensional view. These are some of the instruments that are used throughout the procedures. And we have moved into a wide range of various disciplines and subspecialties for prostatectomy in the urology area, gynecology, and through general surgery, and as I showed the picture earlier, for head and neck. So this slide here shows kind of the evolution of robotic surgery. The stars that I have on there are showing where some of the remote capabilities were introduced, and really surgical robotics got started early 90s with the company that I did work for before I moved to Intuitive Surgical. We merged in 2003, where we had the first FDA cleared robot, and that robot was one that controlled the camera while a surgeon was using laparoscopic instruments at the OR table. That was brought into a remote telemedicine based application towards the end of 2001. The red star was the first remote. It was the transatlantic Project Lindbergh case. As you imagine, there was a lot of data going across the lines. There was the robotic control data, which from the amount of data was pretty small, but then there was video going across, video of the endoscopic view. There was room video that was going across. And so these are all things that, as you start looking at how the surgical robotic system will communicate across the network, there's a lot of different data sources that are required to support the applications. Then as we go up to 2008, That's where we moved into the Da Vinci surgical system, which is the one that Intuitive Surgical markets. And we kind of took a step back and said, all right, we've done some of the telesurgery and some of the remote manipulation, but now let's start really enabling remote capabilities to start driving the business from a servicing perspective. So the ability for our customer support team to be able to understand how the devices are performing, if there are issues with it, and be able to address that. And then also some remote mentoring and proctoring capabilities as surgeons are coming up the learning curve. It's valuable and it's standard practice right now for an expert surgeon to mentor or proctor the surgeon through their training pathway or through their learning curve. So there's kind of four basic aspects when we talk about robotic systems. There's the platform, which is kind of the method of delivery, and that's the patient side cart that I had on the previous slide. That's just what is going to deploy the instruments for the surgical procedure. Instrumentation, talked about that, that's the business end. Then there's training and infrastructure, and this is the area that my team really focuses on, and we're really starting to move towards a network-based capabilities, whether that's servicing, whether it's a proctoring where you need real-time audio video, or if we start then deploying remote updates for some of the features that we have in our simulator. It's a VR simulator. We're going to start deploying updates to that so we can add content as we start training surgeons on different techniques. So I'm going to walk through, I'm going to kind of start with the big picture of some of the telesurgery activities that we had, and then I'll kind of move to some of the more current applications. I always like showing this slide because this was kind of the prototype of the system that actually did the procedure from New York to France. And as for engineers that like a lot of wires and prototypes and things that look like they'll never work, this is how it started. And clearly it was brought up to a little bit higher bar in its design and robustness prior to use, but this was the basic system. You can see the stuff sitting on the cart. That's where all the network communication occurred. So it would take in the analog and digital signals from the robotic system. It would do the necessary conversion to the IP and send it across the wire, and then the other side would invert that. So there is sound to this, but I don't really have it plugged in, and just kind of hard to hear, so I'm just going to kind of talk through it. But this is the surgeon that works at IRCAD in Strasbourg, France. He's actually in New York performing this procedure, and so you can see there he's got a microphone on, so you've got full audio going back and forth between the OR. The endoscopic view that he's looking at is what he sees either from the room camera, which you saw there, or what he's looking at inside the console is the actual endoscopic view. And during this one, there was just a 2D endoscopic view, so the video wasn't a significant amount of bandwidth. And as I mentioned earlier, we've moved forward and now we have full 3D view in HD quality. And so as you start seeing the amount of information going across, it's significant amount more. After that, kind of one-off remote procedure that was done, there was a surgeon up in Canada that ended up doing a total of 21 robotic procedures across the network that was laid out through Canada by Bell Canada. They had put together a network that they called surgical grade. The idea there was that you were able to provide some layer of reliability and quality of service with it, and you were able to assign priority for the various data streams that were going across the wire. So there was a bunch of different procedures done, 21 in total, and it was a pretty good success from that standpoint. No patient harm, no intraoperative complications. And so it really demonstrated that these types of applications could be done in a safe manner and could benefit from a clinical perspective. We took this in 2005, 2006, applied it to the Da Vinci system where we had the 3D view going across, and did kind of the first evolution of the configuration where we had the dual consoles. You remember back on the slide, of the Da Vinci system and had the dual consoles. This particular activity had one remote, one local, and you had the two surgeons working together simultaneously. So now I want to focus on some of the capabilities that we have today, and unlike some of the telesurgery activities which were done in small numbers, we've got now a servicing network that services, we've got over 2,000 robots installed worldwide. I think our servicing network is up to over 1,800 right now, so our devices are constantly communicating in, and it gives our customer support team the ability to understand what's going on. They've got a product support dashboard, as you see on the right-hand side, that they can connect in. They can see what systems are communicating. They have some diagnostics application that they can go in and understand what's going on with the system. It's had a pretty dramatic impact on our business and how we service the systems. Our implementation is what we like to call a phone home. And so on the left-hand side, obviously the Da Vinci system lives inside the hospital network, and so it's not something that we address it directly through the network. It communicates out of the hospital network to the server infrastructure, and then that infrastructure goes ahead and brokers a communication between our product support team and whatever system they need to communicate with. And so that was one way that we designed the implementation and trying to address some of the security and some of the concerns that they have at the hospitals. Another capability that we're just starting to drive and roll out is our remote mentoring or remote proctoring. This particular setup, it has a similar architecture to our servicing, where you have the system is where it gathers and captures the data, the audio and the video, and communicates it out to a remote user. That remote user is typically sitting behind a PC. And so they're able to see what's going on in the OR, communicate back and forth, telestrate on the endoscopic view so that they can collaborate what's going on. And a lot of these use some of the standard, real-time audio transfer, RTP, RTSP, to be able to transfer that across the internet. These types of applications don't have the custom networks like the telesurgery did. We're trying to leverage the internet so that we can have a scalable solution, and it's something that we can build on top of what's already there. And so some of the issues that we need to take in consideration are ones that are typical, whether or not it's our application or just a desktop telecollaboration type of tool. Just another slide here, just demonstrating that one of the things that we found in some of our early trials is you need more than just the endoscopic view. You need room views, you need to be able to see where port placement is done, and the OR staff is a big part of the robotic procedure and how effective it is. And so typically coming across, you've got multiple different video sources that you're switching back and forth between, different nodes on the ends as far as audio communication to be able to enable it. So as we look into the future of kind of what we'll be doing from the robotic standpoint to help surgical techniques out there, the one that's most relevant to this group is probably the bottom right hand corner. The idea is with these systems we can network them as we've done, communicating back to a central server, but the idea of being able to have one surgeon on one console helping to train another surgeon on another console is compelling. And so being able to have the systems communicate kind of as a mesh as opposed to a client server based is something that that is compelling from an application perspective. And likewise, these are things where we can also, from a simulation and training perspective, we can send down virtual reality types of trainers over the network and be able to enable a lot of capabilities that it's difficult, or on a much timely fashion than we could if people had to run around updating software and whatnot. So I'm going to just kind of introduce the concept and then have John come up here and talk about some of the details. When we look at our development, we're obviously an FDA regulated medical device company. And so we walk through and we have a very rigorous design life cycle that we go through. And it starts all the way from our requirements to our test cases and whatnot. And so one of the things that we've been looking at is as we test our system, you can kind of see that when we look at the remote applications, these are in order of importance what we're looking at when we test. And so a lot of the remote capabilities are auxiliary functions. They're not required, unlike the telesurgery where the link is in critical path. Some of the servicing and mentoring aspects aren't in, the network's not in critical path, so they're auxiliary type of capabilities. And so we really look at it all the way from design in isolating that functionality onto separate hardware, into separate software processes, so that we can, isolate the exposure for any sort of issue that may occur, so that the rest of the system can operate and drive the robots, and all the control systems that are on there can function in a different space. So that's really our primary mode. When we go in and test, we need to confirm that. And so that's one of the things with CodenomiCON's products and the fuzzing. We started to integrate that into our testing platform and methodology, so that we can really look at it and use that type of technology to start addressing that question even more for the network-based capabilities. And then when we get down there, obviously we're building in these capabilities for a reason. And so we wanted to be reliable and robust, but we do have very stringent checks inside of the embedded system, especially for some of the network communication, where if it doesn't understand what's going on or receives a packet that it doesn't recognize, if that occurs, then it will just shut down its network communication, not communicate out any longer until the system goes into a different state. And so ours is patient safety, making sure it doesn't impact the system, but then clearly we want to focus on having uptime associated with with our applications that we have built in there. So just a quick overview of how we got into to realizing that fuzzing was something that we needed to bring into our into our testing scheme. We had our systems in our remote servicing application, where we were just finding that they would just drop off the grid, and so they typically communicate up at some periodic duration. And we were just noticing that some of them weren't communicating, and the way that it was being resolved is we'd get one of our field engineers, they'd go and they would just power cycle the system and it'd start working. And so we were trying to understand what that was. And so to address that uptime and trying to make sure that those systems were online, so our customer support team had the benefit of the servicing capability, we found CodenomiCON, we brought in their test suites. And what we found was that when we used the DNS server suite, and we had our system as the DNS client, we were able to go through all the different variations of DNS responses, and we found that there was a certain signature and a certain class of responses that the client, DNS client, was unable to parse. And so then our safety systems kicked in and said, oh, I don't understand this, and then the system would just stop communicating. And so one thing that I forgot to mention was that in our systems we've got our embedded implementation, and since we have a real-time requirements, we try to minimize the footprint of the majority of the software modules. And so with this, a lot of the parsers and whatnot that are done are very small footprints, and so they're not the full-blown implementation. And so we found that as we've started using these tools, we've been able to learn exactly what they're good at and what things they're not able to handle very well. And so what it allowed us to do was very quickly. Took a little bit of time because our system only checked in, I think, every 10 or 20 seconds, and so took a little bit of time to go through that whole DNS suite when we had to do our DNS requests. But we were able to find that signature. We were able to dig into the software and figure out why it wasn't able to handle that and ultimately fix it. And so with that, I was pretty much sold that fuzzing was something we needed to integrate into our into our everyday stuff. And so that's kind of the path that we're on right now.